how do you measure something that's really, really small? Well, first you might try measuring tape, then calipers, and if you've got a big budget, you might treat yourself to a scanning electron microscope. But there is one very clear problem with all of those solutions. A, they're too small, and B, they don't use lasers.
At Ligo, they had the right idea. So by shooting a laser 4 kilometers down this tube, they're able to get an accuracy of 1/10,000th the charge diameter of a proton. That's like measuring from here to the closest star with the accuracy of a hair. Which, I don't know, I still don't have context for that, but it got them a Nobel Prize for physics, and they were the first ones to get gravitational waves detected, so awesome.
Gravitational waves happen all the time. Every time a mass accelerates, waves ripple through space-time. So like, I'm actually waving space-time right now. But it only really becomes noticeable when crazy massive things start accelerating, like black holes colliding. When Einstein first predicted gravitational waves in 1916, he thought they were a problem with his algebra. And then later, when he believed that they were real, he figured it would still be impossible to detect them. But of course, that hasn't stopped people from trying.
In the 50s, Joseph Weber first tried to detect gravitational waves using the 6,000-pound chunk of aluminum. The idea is that it would resonate when gravitational waves went through it, and that would be picked up by these piezoelectric crystals on the top.
Unfortunately, it just wasn't possible to get the precision needed. In 1972, though, Ray Weiss wrote a paper detailing just how an interferometer could be used to detect gravitational waves. Basically, he wrote, a laser beam could go through a beam splitter and then down 2 4-kilometer-long tubes. At the end of each of these tubes would be a mirror that sends the beam back where it would be recombined by the beam splitter and then measured. Normally, when recombined in this manner, the two beams would destructively interfere. But if a gravitational wave were to pass through the detector, it should physically distort space and time, causing the length of the two arms to very slightly change compared to each other. This would change the interference of the two beams, ultimately changing the signal on the photodetector at the end. In 2002 then, Caltech and MIT joined forces to create iLigo, a proof that this could work. And after extensive research and an upgrade to advanced LIGO, we were able to successfully detect gravitational waves in 2015. And by we, of course, I mean humans as a species, not me. I wasn't involved.
So behind us is the beam splitter. So it comes from the laser room back there, which is why we have to have these laser glasses on. It gets split right around here and then gets sent off the arms that way and that way. It then travels back in and is detected over there somewhere.
Unsurprisingly, taking measurements that precisely in the real world is a lot easier said than done. Any particles in the air will cause the laser to scatter, and although they're only sending 20 watts of laser energy, the way it works is to have the beam trapped as a standing wave inside. So after 300 bounces or so, that amplifies it to about 10 kilowatts. With power like that, even a tiny speck of dust on the lens could absorb enough heat to permanently damage the lens, meaning that the 4-kilometer tubes, or the arms, have to be under an ultra-high vacuum.
So this is the concrete that goes around the arm. It doesn't actually help with the laser tube, but it's just to protect it from like cars, animals, stray bullets or whatever. The real magic though happens in this 3mm thick stainless steel tube, which is held to 1/trillionth of an ATM.
Even the vacuum outside the International Space Station can't hold a candle to what they've got going on in here. So how did they build it? Well, first, they cooked. Or more accurately, baked. Now, if regular stainless steel was used for this, hydrogen and other particles on the metal could contaminate the vacuum. So to combat this, every inside surface needed to be heated to 190 degrees Celsius and held there for an extended period of time. Now, for the nuts and bolts, that's pretty simple. I mean, I could do that with my toaster oven at home. But for something this large, what they had to do was pump a quadrant of it full of electricity, effectively using the resistance of the metal to turn it into a heater and hold it at 190 degrees for a month, with the vacuum pumps running to remove all the contaminants. I guess that's probably why they wouldn't let us inside. We are the contaminants. So that's cool. Now the laser can make its way from one end to the other. But what about the mirrors on the end? Even something as small as a truck on the highway or an earthquake in Taiwan would create too much vibration for gravitational wave detection. Which I guess is probably why they put their air conditioner way off away from the building rather than up on top of it like normal people. This is one of the mirrors from Ligo. To reduce the high frequency vibrations, the mirror is hung like a pendulum by this steel wire, and the lower frequency vibrations are decreased by the springs on the lower base. But they obviously weren't done there. In the newer version, the mirror is hung from 4 pendulums by glass fibers. And that is far from the end. On the bottom of the table, there's actually a seismometer that measures any movement in the ground and then uses that information to manipulate voice coils and static electricity to actively cancel out the vibrations coming from the ground. At this point then, the mirrors are basically perfectly still, but they still aren't done yet. For some frequencies, their level of accuracy is being determined by quantum mechanics and the Heisenberg uncertainty principle. But even this can be reduced using quantum squeezing. On a very basic level, they can only know so much about the amplitude or phase of the laser light. But for this application, the amplitude of the light being detected matters a lot less. So they're able to perform a quantum squeeze and get better accuracy out of the phase detection. So they're using a KTP crystal, that is a potassium titanyl phosphate crystal, and this is able to transform 1 green photon into 2 infrared photons, or vice versa. Energy is conserved here because the infrared light has less energy than the green light. So what they do here is pump a crystal full of infrared light. This is just to get a lot of green light, and high-powered infrared lasers are easier to get. And then that green light is sent into another KTP crystal. But when those photons are emitted, they are quantumly entangled. Now in a vacuum, there naturally exists a lot of noise, particularly when there is very little light, like around the dark end of the detector. So by injecting these entangled photons, they're able to remove the completely random vacuum noise and replace it with the entangled photons that produce noise that they like. Now you're probably thinking, I am too, holy sweet crap! How could they even verify that these are actually gravitational waves they're detecting? And the answer is by building another detector on the other side of the country.
Why build one when you can have 2 at twice the price?
So that if a gravitational wave is detected, they can confirm that it isn't just a localized movement. Oh, and also by using 2 observatories to try and find where the astronomical event is happening. So, with the accuracy of the interferometer mostly figured out, how the heck do they acquire all the data and process it? Ah, yes, my friends, we are finally getting to the computery part of the video. In here, they collect data from 250,000 channels simultaneously, and then to isolate the signals being created by the detector from the computers, they actually put the noisy bits of the computer, CPUs, power, etc., in another room 150 feet down the hall, and they connect them using fiber optic PCI Express extenders. The most important thing with the computing here, though, is timing. So every processor's clock in this server room is synced using a custom-built system, since the processor's timing has to be precisely known in order to calculate the time of events in the interferometer. But it's not just synced in this room. There are also computers at the very ends of the laser arms 4 kilometers away with their clocks perfectly synchronized too, and the 22 microsecond transmission time delay taken into account. Oh, and that second gravitational wave observatory in Louisiana? You guessed right, the processor clocks are perfectly synchronized there too. Once the data is collected, it gets sent over to their server warehouse for analysis. And very quick analysis is important, since if there's a large astronomical event taking place, they'll detect it here first, and then they need to be able to tell their astronomers where to point the telescopes in a timely manner. So all that processing is handled in here, where they've got 6,000 processing cores, 64 GPUs, almost 4 terabytes of RAM, and close to 5.5 petabytes of data stored on SSD, spinning, and tape storage. The data is then copied from here to Caltech servers, where it is further analyzed and made available to more scientists, and then eventually the armchair physicists at home. And they're still not done. Further plans to improve their accuracy involve using cryogenics to reduce the movements of the molecules on the lenses, detecting changes in the Earth's gravity to remove noise from movement below the Earth's crust, implementing quantum squeeze that can be changed throughout the frequency band, and even building a space-based gravitational wave observatory. The goal is that with every little adjustment, they should be able to see even further into space, collecting a bit more data about how our universe works. So a huge thanks to Ligo, and particularly Amber, you rock, for letting us come and hang out in the observatory, and a huge thanks to you guys for watching. So thanks for watching, guys. If this video sucked or you're a member of the Flat Earth Society, you know what to do. But if it was awesome, get subscribed, hit that like button, or check out the link to where to buy the stuff we featured in the video description. Yeah, right. Also linked in the description is our merch store, which has cool shirts like this one, and our community forum, which you should totally join.